right? Does that make some sense? So these are called optimization problems. You'll be doing these later. Students aren't big fans of them because they're word problems. But that's probably the most applicable thing. Any function out there in the world that you want to find highest and lowest points of, we can use calculus to do it. All right? Okay, I hope that gives you like some at least small glimpse into Cal 1. We're obviously going to do a lot more than that, but okay, I've left myself a little bit of time. Y'all ready? Review? All right. This is going to be a very brief review. I'm not going to get into too much detail. Where are you? Calculus, I said, was, there's two fathers of calculus, Newton and Leibniz, right? I mentioned that. What I've always found very fascinating is that they developed calculus independently of one another. So they didn't know that they were doing calculus. Imagine that you're trying to work on something, okay? And the mathematics to do that doesn't exist. So you have to make up the mathematics. That's what Newton and Leibniz were doing. And they were doing it at the same time, period in time, in different parts of the world. And then found out later, oh wow, we're doing the same thing. So in this class you'll see we have different notations for things. And sometimes we use Newton's notation and sometimes we use Leibniz notation. So I'm sure all of you have heard of Newton, right? Newton gets a lot of credit because he did a lot of stuff with the laws of motion and stuff. Leibniz doesn't get as much credit, but you know, he was also the father of calculus. So there's a famous quote that Newton has. I don't know if you've heard it before. Says, he said, if I've seen farther or further, I'm not an English major, if I've seen farther than others, it is only because I've stood on the shoulders of giants. Have you all ever heard that before? So basically Newton was even working off of other people's work, and then he just took it and created the calculus. Pretty amazing. All right, here we go. Inverse trig functions, 3.5 out of the book. Wait a minute, hold on. This is Cal 2. We don't want to do that. Oops. Okay. All right, here we go. Functions and limits. This is chapter 1. The first section. Now look, do not sit here and try and copy everything I have on the board down, because this is all on Canvas. You can print these notes out. This is just for us to discuss. So can you all read that okay? Should I maybe make it a little bit bigger? That a little better? Okay. So we learn in college algebra, a function is a rule that assigns to each element x in a set D exactly one element called f of x in a set E. So a function takes, in our case, takes a number, spits out a number, right? Input, output. The inputs, okay, the things that can be plugged into a function are called the domain, and the outputs of the function are called the range, right? So all the things that come out the other side, the range. Now, whenever we talk about functions, we have something called an independent variable and a dependent variable. So let me give you an example. If we have f of x equals, let's just go with the line 2x plus 1, then here we normally, when we go and graph these things, we replace f of x with y. That's something that we have been doing for years and years, right? So in this case, if we write it like this, it is understood that f is a function of x. And that means x is the input, which means that x is the independent variable. And then when we write it this way, we would say y is the dependent variable, because in order to know y, you must provide x, right? Someone gives you x, then you know y. So independent, dependent. All right, graphs of functions. When we first started to learn how to graph a function, we did these things called t-tables. Remember that? You do like, and then you start plugging in numbers and put all these dots together, right? And we graph these functions. What I want you to understand is that the graph of a function is just all those points, right? Like making a t-table. You just keep on doing more points, and if you could do all of them, right, which would be impossible to do, but if you could plug in every single point out there, or every little input out there, then you would get a curve, right? But really it's all these points. So it's a bunch of inputs and outputs visualized. All right, some important things about the output or the function. When we talk about an output, like right here, this right here, that is some f of x. That's f of x is an output of the function, and f of x will always be the height of the function there. It's how tall it is, right? It's how tall that function is at that input. It's how high the function is, or if it's below the graph, it's how low it is. Okay, so here's another way of visualizing that. Make this a little bigger. If this seems very too low level for you, then just hang tight, okay? So I'm going to move this graph around here, and what you'll see is the green is giving you the x, right? That's your x coordinate. That's your input, and then that's your height. Yes? So right now, the function's value there is positive, right? The function's value here is what? 0. The function's value here is negative, 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 negative. Function's value here is positive, right? Okay. Now, remember the vertical line test? Vertical line test is what you do when you look at a graph of something. You run the vertical line test to determine whether or not it is a function. And what has to happen is this vertical line that you use, you can only hit the graph one time, right? So like here, this would pass the vertical line test, wouldn't it? Yeah. Okay, so that is a function of x. If we switch to this, is that a function of x? It is not, because it will fail the vertical line test. It doesn't fail here. This is fine. It's when we get over here. Now we have a problem, right? Okay, so this is not a function of x. Is it a function of y? Yes. It is a function of y. That means you would go and do the test the other way. We're not going to get into that right now. All right, remember piecewise functions. These are functions that are defined or written this way. So it's like it's a certain function on one part of the domain and then a different function on another part of the domain. So like here, as long as our x is to the left or equal to 1, we're going to be this parabola that opens up. But if we're to the right of 1, it's going to be this parabola which opens down. So you can kind of see the two pieces of this piecewise function here. You all remember seeing that, college algebra? We'll be doing more with piecewise functions. All we're trying to do here is just try and stir all this stuff back up. Make sure we have some terminology down. All right. Intervals where a function is positive and negative. So we could read through this, but let's just look at the picture because I think it makes more sense. Take a look at this function. All right, let's talk about where it's positive. And I think I should make this a little bit bigger. Okay, so where is this function positive? And let's ask someone. Jamie? Where's Jamie? Hi, Jamie. How are you doing today, Jamie? Great? Okay, so if I were to ask you, where is this function positive, can you, like, in words describe what it is I'm asking you for?
So, I guess on the graph or above 0?
Yeah, okay, so you said above 0, right? Let's be more specific. Where it's above the x-axis. I know that's what you meant, but 0, there's 0 this direction or that direction. So what you mean is, if I say where's the function positive, we're saying where's the function above the x-axis, right? So would you agree Jamie, that it is right here and then over there, right? But when we ask for the intervals where the function is positive, we are talking about the x values. So we're referring to, like, if you plug an x in anywhere in here or anywhere over here, it's going to spit out a positive answer. So your answer to that question is actually an interval on the x-axis, right? So it's all the numbers between, it looks like -2 to 0, and all the numbers from 2 and on. And so our answer would look like this. Does this notation look familiar to you? Parenthesis, -2, 0, parenthesis, union, parenthesis 2, infinity, parenthesis. Why are there not brackets? So if I were to have written this, union, okay, this would mean include -2 and 0, right? Why am I not including those? That's right, because at those points, I'm on the x-axis, and when you're on the x-axis, your value is 0, and 0 is not positive. 0 is negative. No? 0 is neither, okay? 0 is not positive nor negative. All right. Is 0 even or odd? 0 is even. 2, 4, 6, 8, 10? Go backwards. 4, 2, 0, -2, -4, those are all evens. So 0 is even, but it's not positive nor negative. That's just a side note there. All right, so where is it negative? Now we're asking, where is it below the x-axis, right? So now everything's going to change. Now it's everywhere over here, down, between here and here, down. And so our answer changes a little bit. Do we ever put brackets on infinity? No. Okay, because infinity, remember, is an idea, right? It's the idea that it continues forever. It's not a number. I taught my daughter that when she was like 3 or 4. I was like, she asked me what the biggest number was, and she's like, I heard it was infinity. And I'm like, it's not. I don't want to ever hear you say that again. So infinity is not the biggest number. Infinity is an idea. There is no biggest number, all right? Okay, so our interval changes. Now, where is it 0? Now we're talking about actual numbers on the number line, right? Boom, boom, boom. And look at how our notation changes. Instead of using parentheses with these unions, we use braces with numbers with commas. So that's the notation that you use when you want to have a set of numbers as opposed to an interval. All right, so function positive, function negative, function 0. Got that down? All right. Now, how about where a function is increasing versus decreasing? So now we're talking about up and down as you read a book from left to right. It's always read a book from left to right, okay, when we talk about this. So when we're talking about a function being increasing, we look at this one here. This would be an increasing function, right? As I move to the right, the property is this. It can get kind of messy when you really start to get technical about it. But to be increasing means that if I have 2 points, right? This points to the left of this point. So point 1 is to the left of point 2. Then the height at this point needs to be lower than the height at the other point. Right? That's what it would mean for a function to increase. And that's what, if you go back up to the definition, that's what this is saying, increasing. I know it doesn't look that nice when you read it that way, but it's saying, look, if point 1 is to the left of point 2, right? Then the height of the function at at that first point is smaller than the height of the function at the second point. That's all this means. And then if you want to say it's decreasing, it's flipped. So if the point 1 is to the left of point 2, now we need it opposite. We need the height at point 1 to be bigger than the height at point 2. And you get this picture right here. I don't want to complain about these boards because our boards really sucked until they put this stuff on it, and now I can't use my mouse. So point at the first point, second point, right? First point's to the left of the second point, but the height at the first point is bigger than the height at the second point. If that ever happens, you have decreasing. And then what about constant? A function that's constant? They're going to be equal. Okay, so regardless of where the points are, your outputs are always the same. So as you move from left to right, you've got nothing happen, no change. Okay, so if we look at a function like this now, can we determine where it's increasing and decreasing? This is a little harder to see, I guess, but okay, so I'm going to call on somebody. Who's the lucky one? Is it Owen? Owen? Okay, Owen. I'm just going to put my marker here, and we're going to read this left to right. So I'm going to start drawing on the graph. So I'm obviously doing what here? Increasing, increasing, right? Increasing. Until I get to where?
-1.
Right up here, right? That's where it starts to change, right? And now at this point, I start to decrease, 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 decrease until I get to here, and then I start to increase again. So what I've highlighted here in blue, blue on top of blue, sorry, everything over here, the function is increasing, and from here, it's increasing. Everyone follow that? So again, our answer to where it's increasing is not y values, it's x values. We want to know the x values where our function's increasing, and our x values where the function's increasing over here. Ignore the fact that these are all complicated. It's basically saying negative infinity, which is forever, all the way till you get to some number, and then unioned with from some number on. Okay? How would we ever find that number? Because that's this one, right? How would we ever find that? Well, that's why we're here, okay? We will find that later. We will be able to take, if I give you that function in about 4 weeks, you will be able to find that point right there and tell me where that highest point is, all right? But right now, we just need to understand what the picture looks like. Increasing, increasing, and then our decreasing part is just that part in the middle, right? This, where'd it go? Yeah, it's right here. From here to here, it's decreasing. So just that little interval is the only place where our function's decreasing. And then what about constant? Well, I don't know why I had that there. I think I just copied some of that code. By the way, if any of y'all are any CS majors, computer science, only a few, all of these animations that I'm using, I'm using a program called Wolfram Alpha, which is C+ based language. So it has so many built-in functions that I don't even consider myself like that this is real coding. But if you're interested in actually getting your hands on this, I'll share all my code with you if you're interested in it. So I must have like copied and pasted my code and left that one here from the previous example, sorry. All right, so what we've done so far is we've looked at some pictures of graphs, or pictures of functions, and we've just talked about some of their properties, positive, negative, constant, increasing, decreasing. But what if I give you a function algebraically and ask you for domain? So domain is going to be a huge issue in this class. We're going to have to always pay attention to domains. So let's talk about this first function right here. Are y'all doing okay? We've got 20 minutes still. Let's talk about domain. And the lucky one is Marcus. Where's Marcus? I'll try my best with names. Okay, no promise. I'm terrible with names. Always have been. Okay, so if I call you like in 10 weeks from now, if I pull up Marcus and I'm like, Marcus, don't be offended. Okay? All right. But Marcus is my cousin's name, so I think I might be able to do this, all right? All right, Marcus, when I want to determine the implied domain of the function. So how do you feel about that? Iffy. Okay, iffy. So domain is the stuff that you're allowed to plug in, right? So when you look at this function, is there anything that kind of like jumps out at you as a potential problem that we would run into?
Dividing by 0.
Dividing by 0, right? So what you would be interested in is what would actually make that denominator 0, right? So then you would just set up that equation, and you actually don't want that to happen, right? But in order to figure out where we don't want it to happen, I'm actually going to figure out where it happens, right? So let's figure out where this happens, and we'll throw those out of our domain. All right, Marcus, do you feel comfortable with that? So how would you do that, Marcus?
Solve for x.
Okay, how would you solve for x on that one?
Subtract 8 from both sides.
Okay,
X squared plus 7x equals to negative 8.
and
And then probably
it's all right.
x.
Okay, I'm going to go down that road. Remember I said this in the beginning? I'd rather you make a mistake here than on a test, right? Okay, so we're going to go down the road, and look, this is very important, everyone. I don't want anyone to leave here feeling like I'm trying to, cause you grief, all right? That's not the point, all right? The point of this is that what Marcus is doing is something that a lot of people do that is not going to work. And we need to talk about why it's not going to work, all right? So Marcus, is that step legal?
Yes.
Yes, there's nothing wrong with that. Absolutely nothing wrong with that step, all right? Then you said factor out an x on the left. Okay, can we factor an x out of the left side? Okay, nothing wrong with that. You're all good to go. However, the next step, hold on, I've had a couple of people raise their hands. The problem here, Marcus, is what do we do now with this? If the temptation is to set x equal to negative 8 and x plus 7 equal to negative 8, if that's, I'm not sure that's where you were going to go, but that's what I've seen students do, this would be the mistake. And the reason why is because the only way that you can ever have x times x plus 7, to be able to split it up into two equations is if this side is what? 0. This has to be 0 for this to work. Then you can set each factor to 0. It's called the zero factor property from college algebra. So you can only set factors equal to, set them into separate equations if the right side of your equation is 0. If it's 8 or negative 8, it's not going to work. Let me try and explain it this way. What if I tell you that I have two numbers, everyone, and they multiply to be 0? Okay? One of them has to be 0. Has to. There's no way you can make that work unless one of these is 0. Now, let me do it another way. What if I tell you two numbers multiply to be 4? Does one of them have to be 4? No? Can you give me an example of two numbers that multiply to be 4 where neither one of them is 4? 2 and 2 would work, right? Right? So if you have two things multiplying together to be something other than 0, it is possible that this doesn't have to be negative 8. This one doesn't have to be negative 8. That one doesn't have to be negative 8. Does that make sense? Okay. So instead, Marcus, when we look at this, you actually have like a couple of options. One is to factor right now, or what's the go-to if for all quadratics quadratic formula, okay?
It's supposed to be negative 8.
Was it negative? Oh, did I write? Oh, that's my mistake. Okay. Sorry about that. Is that what everyone was saying? Sorry about that. That doesn't change the, yeah. Okay. Oops. I made my first mistake. Yeah, y'all, I guess I should have said raise your hand if you see that, but you did, and I ignored you. Sorry about that. I thought y'all had something else to say. Okay. So here, factor. So this should be what? Minus 1, x plus 8. Okay, so this factoring right here, everyone's coming in here at a different level. Okay, I can tell you that from my experience, which I have a lot of. Everybody in here has a different comfort level with factoring. All right, I will tell you that my expectation is that you can do this step. All right. Maybe you need to like brush it up, and now you've seen it. You're like, oh yeah. But if that's causing you an issue, we should talk a little bit about getting some of those skills in order first. Okay. Right? Okay. So what is the domain? What is the implied domain of this function? What we've said is that we don't want this to happen, right? If we plug in 1, we're going to get division by 0. If we plug in negative 8, we're going to get division by 0. So how do we write the answer? Everything except these numbers, right? So I like to visualize this on a number line. If we've got negative 8, make sure you put these in the right order. Those are the two numbers we don't want, right? So I don't want that one. I don't want that one. I do want everything over here. I do want everything in here. And I do want everything over there, right? So there's an easy way to do it and a hard way to do it. Elijah?
Yes.
I heard yes. Yes, Elijah? Any idea of how we could write that in like interval notation?
Would be negative infinity.
Negative infinity, parenthesis in front of it, right?
Yes.
Comma,
To negative 8.
to negative 8, parenthesis, union, parenthesis.
1.
We need this stuff too.
Negative 8.
Negative 8 again, to 1,
To 1.
to infinity. There we go. That is the, so you could, that would be acceptable to me. You could also put x is an element of that set. You don't need that, but if you put it, great, okay? That's a nice way of doing it, right? It's kind of ugly, but it's like everything up to negative 8, jump over negative 8, go to 1, jump over 1, then go from 1 on, right? All right. Another way you could do this is just say x is not equal to 1, x is not equal to negative 8. But that's not really a set notation, or an interval notation, but you're communicating the idea, okay? It's like everything except that. All right, let's move on to g of x. Uh-oh. I'm going to go with Sienna. Yeah, is that right? Did I say it right? Sienna. Okay. I'll do my best. I'll do my best. G. Sienna? Sienna. You sure you didn't just switch it on me? No. Okay. So looking at G, do you see any issues with G? Okay, so the radical. What do we know about radicals? You can't do the square root of, you can do square root of 0, right? Square root of 0 is 0. But you can't do negatives, right? Can't have a negative. So we have a problem here. This function right here, we would run into an issue if what was underneath here was ever negative or 0. And I just told you 0 was okay. But what's wrong with 0 in this case? If this was 0, then you would have division by 0, right? So if it was just the radical and the radical was not in the denominator, a radical by itself, we would just want to make sure it's greater, and not negative. But in this case, we want to make sure that this, what do we call the thing inside of a radical? It has a name, actually. It's called the radicand. Okay, so the radicand must be greater than 0. Must be greater than 0. Everyone understand why? If it's negative, you have square root of a negative number, can't do it. If it's 0, then you have division by 0. Now, Marcus, the problem I asked you about, Marcus, that was a quadratic equation. That's what we were looking at, right? Jesse? Where's Jesse? Jesse. Do you know what we call this? I'll give you a hint. It's not a quadratic equation. It's called something else. If you don't know, it's okay. I mean, you can just say, I don't know. Not sure? Anyone know what that's called? Quadratic expression. An expression would be something that doesn't have like an equals or a greater than or sign. That would just be like, that's an expression right there. Quadratic inequality. Okay, it's a quadratic, but it's not an equation, it's an inequality. And how important is it to us that that's this symbol as opposed to an equal? It's night and day difference. The method that we use to solve this is completely different than the method we use to solve a quadratic equation. And you need to know that. Like, you know, we need to recall that, hash that back up. So does anyone recall the method for solving a quadratic? I'm just going to put quadratic ineq, okay? Quad ineq, quadratic inequality. Anyone know the method for this? Take a shot. Anyone have? Al? I thought I saw you raise your hand. Yeah, go for it, Al.
Well, what I do is I just momentarily
Uh-huh.
make it an equation,
Okay.
and then factor it out, and then identify those 2 points.
Okay, so you're saying we're going to kind of like temporarily act like it's an equation, and then figure out what would make this thing equal 0, right? And somehow use that to figure out where it's bigger than 0.
Right.
Okay, I like that idea. Let's go with this. We take this as an equation. Now this one right here we can factor using the GCF. Just pull out an x out of both of these. And while I've got this here, let me. I hate this. Try and do something real quick. Oh. Where's my little chart? I don't know where my little chart is. Okay. So just to do a quick poll right now. How many of you feel like what I've talked about so far, you feel good, yes? You feel not so good, no? Okay. All right. Oh, you don't want to be the, they don't want to be the 2 there? Okay. All right. The whole idea is that's supposed to let you not feel the pressure of being the one that is not understanding it, all right? All right. Oh, okay. Thank you, thank you. All right, so we solve this, we get 2 answers, 0 and 4. I'm going to trust that you can do that, right? All right, Al, do you want to keep going here? Because
Next thing what I do, I just do like a number line like you did before,
okay,
and I plot those 2 numbers,
okay.
and I draw open circles above both of them because I know I cannot include that.
Okay, so you're saying because there's no equals under this, you don't actually want these to be part of your answers, but they're important because it's something is happening to the left and right of these. Okay, keep going.
So now what I do is I take test point to the left of 0.
Mm-hmm. You just like test a point, just like pick some random point over here?
Like 1,
Like
negative 1.
-1? And what do you do with that point?
I take that and I can plug it into the original one.
Like in here,
Right.
and see what happens. So what would happen if we plug -1 into here, everyone? What would happen here? -4, and then be real careful there. What's -1 squared? +1, right? But then you're subtracting it. So we have -4 minus 1. That's a negative number, right? And is a negative number bigger than 0? No. So Al, this didn't work. So what does that tell you?
That tells me as I go to the left of 0, I'm getting negative numbers.
Nothing works over here then. Okay, so that means nothing would work here. Yes?
A question on 4?
Yes.
X shouldn't be -4.
No, because you have to set 4 minus x equal to 0, right? And then just like add x to both sides. Yeah, if it were flipped, then yeah, it would have worked. Okay, so you're saying that it's like, okay, now I know like if I look at this as like a number line, like to the left of 0, nothing here works. Okay? And then you just keep testing points?
Well, I'll just test one from, well, 2 more. One from the left of 0, I'll just choose 1.
Like, so another one here and maybe another one here?
And another one right there.
And check those and plug them into here and check again. And what you'd find is that this would work and this one again wouldn't work. I like that method.
Then that's right there, my interpreter.
You learned that in college algebra, I guess? Or somewhere? That is the way you should do it, okay? I mean, that is the correct way. Now, there is a shorter way, slightly shorter, slightly shorter, in a way that I like. This is the way I teach it, okay? I teach it this way, all right? But there's a slightly shorter way when you get to this point right here where you get these 2 answers. Let me show you the slightly shorter way. Slightly shorter way is that, look, at 0 and 4, we know something's interesting, right? We don't want to include these answers. And so all I want to know is when this is true, right? Yep. Now, what is that graphically? Quadratic. Which way does it open? down, right? This is a downward opening parabola because there's a negative on the x squared. And those two numbers, 0 and 4, are the x-intercepts of that function, right? If I were to look at that as a function. So if I were to ask you to like graph this, you know it would look like this, don't you? Right? And aren't you asking then when that graph is bigger than 0? And you can tell where that's happening. It's happening between 0 and 4. And see, I could do it this way without ever having to test any points. But you have to know what a parabola looks like, which I think you should know. All right, so now our final answer here is everything in here, not including 0 and 4, so that's our domain for G. All the points between 0 and 4. Good? Okay. Who's the lucky one that gets secant? Omar? Where's Omar? Omar, you're up. I've got 3 minutes, Omar.
Yeah, I wouldn't know what to do with the function, honestly. You get 1 over cosine.
Okay, good. That's the first thing I was hoping you would say. Okay, so Omar is saying, all right, we're trying to find the domain of this. So from pre-cal, Omar remembers that that's 1 over cosine of x. All right? And now algebraically, Omar, what do we not want to happen here?
We don't want it 0.
We don't want that bottom to be 0, right? So we don't want cosine of x to be 0. So let's look at when it is 0. So our question is, when does this happen? Because whenever this happens, we have a problem. And now we have the great question. How did you learn your trig functions in pre-cal? So let's think. We don't have a lot of time. We only have 2 minutes. But let's talk. We're going to get to that. I just want to ask a question here. If I ask everyone in this class right now, what is cosine of pi over 6? I'm not asking everyone, never mind. Arturo. Where's Arturo? Okay, Arturo, if I do this, what goes through your brain? Do you think calculator or do you see something? What do you see? Okay, what is that? The unit circle? You see the unit circle. You don't see the graph of cosine. In your mind, you've got a unit circle. And so let me see if I'm correct with this. You're visualizing the unit circle. You're comfortable with the idea that pi over 6 is here, right? 30 degrees. And then what? You've memorized these points. Maybe you don't recall them right offhand, but you memorized that these are like root 3 over 2 and 1/2. And what are you doing? I've asked you what this is. What are you doing with this? You're right, but I'm just saying, like, what's the value of this now? So how are you going to get that answer from this? Because when you're looking at the unit circle, cosine of the angle is always the x-coordinate. And sine of the angle is always the y-coordinate, right? So the x-coordinate here is root 3 over 2. And we're done, right? Okay, now I need to ask the class. Let's take our little poll here. How many of you, where's my chart? There it is. Okay, how many of you think of cosine of pi over 6 in this way? Yes or no? So no no's? Okay, good. All right. That means everybody's working off the idea of the unit circle. All right, good. Then over here, what this is really saying is cosine of an angle is 0, which really means where on the unit circle is your x-coordinate 0, right? Because this is always the x-coordinate. So that happens at here, x-coordinate, right? Here and here. Isn't that where your x-coordinate is 0? This is the point 0, 1. This is the point 0, -1. So that's going to be at, what's that angle? Pi over 2, and then 3 pi over 2, right? I'm out of time. That's incorrect. That's not the answer. I mean, it is, but it's not. The correct answer here is pi over 2 plus pi times n, or pi times k. Now, we'll pick up class with this See, there's an infinite number of solutions to this. In pre-cal, a lot of people are going to say, as their answer, they're going to say the solution to that equation is pi over 2 and 3 pi over 2. And I would say, yes, that's correct if you're restricting yourself just between 0 and 2 pi. But the general solution is this. And that's where we'll start class next time. We'll make sure we all understand how to get the general solutions. Make sure you try and do your homework. You're not going to be able to do both sections because I didn't finish. Try and do as much as you can from 1.1. All right? We'll pick up with 1.2 on Thursday. Have a good day.
Can we just leave the clickers?
Yeah, leave the clickers. I'll pick them up.